Hi, this lecture video is to help you out and understand the next two of the gas laws, Gay-Lussac's law and the combined gas law. All right. Now, Gay-Lussac's law is very similar to Charles's law. However, instead of temperature relating to volume, here it is a temperature relating to pressure. So the pressure of a sample of a gas at constant volume is directly proportional to the absolute temperature. So as I said, it's very similar. Basically, if the volume is fixed and you increase the temperature, instead of the volume going up, it will be the pressure increasing. All right. And that may eventually cause the volume to then go rapidly, and it's what we call an explosion. This right here, by the way, is why you never want to put a sealed can container in a fire or anything like that. Temperature going up will cause the pressure to build up until it exceeds the structural integrity of the can and it explodes, often dangerously. So Gay-Lussac's law, and as you can see, very similar to Charles' law. Only difference is that you change the volume for pressures, okay? But it's done just the same. And once again, since it involves temperature, don't forget that temperatures must always be in kelvins. Now, the three laws that we have learned so far, Boyle's, Charles, and Gay-Lussac's, all assume that, basically they state that one of the variables remains constant, okay? For example, here in Gay-Lussac's law, you have the constant volume, okay? And if you notice, the thing that's constant is not part of the formula, okay? It's not part of the formula there. It is simply missing. Now, if you take all three of those laws and say, well, what if nothing is constant? What if the pressure, the volume, and the temperature are all able to change? Well, in that case, we then use what is known as the combined gas law. And the combined gas law basically is the gas law for a given quantity of gas that is changed from one set of pressure, volume, or temperature conditions to another. Okay? So this one, if you notice, it is a combination of the other three. It is PV over T equals PV over T. With initial conditions here and final conditions here. And you will see sample problems of these as well, where everything is changed. But something else to keep in mind, since this has all of the other formulas in it, this is the only one that you really need to remember. If you have this one down, all the other ones are in it. Basic. Excuse me. Basically, you just use this formula. And if something, a particular variable is not mentioned, or if it is mentioned, it says it remains constant, then you remove it from this formula and use what's left. For example, if, like in the last one, excuse me, if, like, for example, in the Gay-Lussac law, it said that volume was constant, right? So if you have a problem that says volume is constant, you simply remove the V's from both sides, and what's left is P over T equals P over T. So temperatures must be in kelvins, but you can use this law for all problems where the conditions change. You simply remove the variable that remains constant or is not mentioned. All right, so then make sure you watch the sample problem videos so you can see examples of how to do these problems. Thank you. Now this sample problem is for the combined gas law. It reads, a sample of diborane gas, B2H6,
a substance that bursts into flames when exposed to air, has a pressure of 0.454 atmospheres at a temperature of negative 15 degrees Celsius and a volume of 3.48 liters. If conditions are changed so that the temperature is 36 degrees Celsius and the pressure is 0.616 atmospheres, what will be the new volume of the sample? Now for this problem, we're going to be using the combined gas law, which is P1 times V1 over T1 equals P2 times V2 over T2. First step is we list out all of our variables and go through the problem and see which matches up with which. So the first pressure mentioned is 0.454 atmospheres. First temperature mentioned is negative 15 degrees Celsius. And, whoops, that in the wrong place. Negative 15 degrees Celsius. The first volume is 3.48 liters. And then it says conditions are changed so that the new temperature is 36 degrees Celsius and the new pressure is 0.616 atmospheres. And the question is, what is the new volume? Since we're solving for V2, we need to rearrange the formula to isolate it. Remember, when isolating a variable, it needs to be a numerator and all by itself on one side of the equation. It's already on top, so it's already a numerator, so we simply need to isolate it by doing the opposite of what's being done to it. Since it's being divided by T2, we want to multiply by T2. And since it's being multiplied by P2, we want to divide. That way, those cancel out, leaving V2 all by itself. And of course, that also, what we do to one side, we have to do to the other in order to maintain the balance. All right. Looking at our variables, we also need to make sure that all the units match. Atmospheres matches with atmospheres. Liters will match with liters. But temperature also must be in kelvins. So we add 273. So negative 15 plus 273. So we take 273 and minus 15. That's going to be 258 Kelvin. Here, when we add 273, we're going to have 309 Kelvin. Now, we are going to take those numbers and plug them into our formula. So we have V2 is equal to T2 times P1 times V1. So T2 is 309 Kelvin. P1 is 0.454 atmospheres. And V1 is 3.48 liters. All over P2, which is 0.616 atmospheres, and T1, which is 258 Kelvin. Canceling out the units, atmospheres with atmospheres, the only unit left over is liters, which means that's going to be the units of our answer. On my calculator, I'm simply going to go through, if the number's on top, I multiply it. If the number's on the bottom, I divide. So I'm going to go 309 times 0.454 times 3.48 divided by 0.616 and then divided by, because it's on the bottom, 258 equals. Now my calculator reads 3.0718, so forth. But remember, I need to round the answer off so that it has the same number of significant figures as the measurement with the fewest. Looking at all of my measurements that I plugged into the formula, they all have 3 significant figures, so I will round my answer off to 3 significant figures and write 3.07. Once again, the units are liters, and I circle my final answer.